In classical geometry, one talks about elliptic, Euclidean, and hyperbolic geometries. Euclidean geometry lies on the rim between the other two. In the Euclidean plane, the distance minimizing curve between 2 points is a line segment, and each line segment can be extended into a two-sided distance minimizing curve, the straight line. An analogous statement holds in hyperbolic geometry. What distinguishes the two is the postulate that in Euclidean geometry, given a straight line and a point, there is one and only one line that goes through that point which is parallel to the first. Euclidean geometry is critical in this sense, and it seems plausible that parallel distance minimizing curves, either one-sided or two-sided, should collapse into one in a random perturbation of the Euclidean metric. The existence of disjoint parallel distance minimizing curves is closely related to the existence of two-sided distance minimizing curves, also known as geodesics. And we are prone to believe that such curves should vanish in a random perturbation of the Euclidean metric. First passage percolation is a model for a random metric space, which, on a macroscopic scale, induces a norm that's equivalent to Euclidean distance. It's typically defined by adding non-negative weights to the edges of a lattice, and in a planar setting, first passage percolation can be thought of as a random perturbation of the Euclidean metric on R2. In this paper, we address the related question of whether, in a random perturbation of the Euclidean metric, the distance minimizing curve between 2 points can be extended into a one-sided distance minimizing curve. This is equivalent to the question of whether, for a given point V in the plane, there exists a one-sided distance minimizing curve starting at the origin and going through the point V. David Coupier has recently explored this question for certain random geometric trees. For instance, in planar last passage percolation, under the assumption of a strictly concave and differentiable shape function, Coupier showed that this probability decreases to zero as the distance increases. The assumption of strict concavity and differentiability is significant, as it has only been verified in a few integrable settings. The objective of this paper is to show that Coupier's result gives evidence of a much more general phenomenon by establishing the analogous result in first passage percolation. We shall consider a rather general family of first passage percolation models on the square lattice, and let by T0 denote the set of infinite one-sided geodesics starting at origin. We write V in T0 for the event that there exists a geodesic starting at origin, which contains V. Our main result is an analog of Coupier's result in the setting of planar first passage percolation, and says that the probability that a specific vertex is visited by some infinite geodesic starting at the origin decays to zero uniformly in the distance. Identifying T0 with the union of its elements, we may interpret the T0 as the tree of infinite geodesics rooted at the origin. The theorem implies that this tree occupies a negligible fraction of the plane. The method of proof is an argument of coalescence. We shall aim for a contradiction and suppose that for some diverging sequence Vk, the probability that Vk is on some infinite geodesic starting at the origin is at least delta. Considering translates of these events and using the uniqueness of geodesics between endpoints, we obtain a picture that looks as follows. From Vk we obtain an infinite geodesic going through the origin, and from a translate of Vk we obtain an infinite geodesic going through a translate of the origin. Central in this figure is that not both the initial segments and the terminal segments may touch. Working with weak limits, the above observation allows us to construct a shift invariant measure supported on families of non-crossing and non-coalescing geodesics. This contradicts the fact that a typical geodesic is coalescing, as we make precise in the paper.